So today I'm going to talk about mycotoxins and how to use two different methods to calculate how much mycotoxins in your food. One method is called a stable isotope dilution assay, and the other is called a matrix matched calibration method. And in today's presentation, I'm going to cover the following aspects. First, I will briefly introduce the background of mycotoxins and how to use sample preparation to do a sample, then how to do the detection with the LC-MS method. Here, I will introduce some of the challenges faced by LC-MS and also explain what is SIDA, what is matrix matched calibration, what is the pro and the cons for each method. Then I will show you some of the results I obtained from commercialized food matrices and also using two different methods comparison. Then comes the conclusion and acknowledgements. So first, what are mycotoxins? You probably can have a pretty good guess from the name. Toxins means poisons. Myco indicates that they derive from fungus or mold. So they are actually the secondary metabolites released from mold or fungus. So what do? They actually deactivate your immune system, put your immune system into sleep. In that case, they will generate a lot of health problems, such as fatigue, joint pain, skin rashes, or immune suppression, or even cancer. So, what are the causes? Most of the time, they come from the food you're eating, mainly found in corn, grains, beans, coffee, vegetables, fruits, and meats. So if we think about all the processed food we're eating, most of them have some type of corn, especially those GMO corn. So 90%, I'm guessing, you're having mycotoxins. If you're drinking beer, probably you will get mycotoxins too, because those bad grains, like people even don't want them to feed animals, they end up using them to fermentate the beer. So since we all agree that drinking alcohol is not healthy anyway, but whoever thought about drinking coffee could be so dangerous too, right? So the coffee beans during like chopped, dried, and processed, stored, the mold can grow and mycotoxins can be created, right? So there is a special mycotoxin called ochratoxin A. It's very toxic to kidney and it's a carcinogen. It is present in especially in coffee. So overall, believe or not, mycotoxins are there. It's in your life, in your blood, and your diet. Well, after I learned about all the mycotoxins, I always ask myself crazily, am I eating mycotoxins or are my food full of toxins? So before I drive myself too crazy, I decided to do some tests on those commercially available food matrices. So I heard that the core or maze, they are considered to be the most complex matrix with the severe contamination of mycotoxins. So I just bought two types of corns together with brown rice and peanut powder from grocery stores, actually. So in order to prove that the method I will develop is accurate, I also bought two reference material from FAPA's company. So I really will work as a science detective and asking my questions like a detective, you know, what possible types of mycotoxins will be there and at what concentration? Are those concentrations safe and how do we do the detection? So, like with those questions bear in mind, I first found the 12 most regulated mycotoxins from literature and from published work. Here are the chemical structures of those 12 chemicals. As we can see, they are all small molecules, polar, chemical stable, and also they are temperature resist. Clearly, While a lot of the countries or most of the countries, they have a very stringent regulations on those compounds, obviously, for obvious reasons, right? So regulation levels, they vary from country to country, like agency to agency, but all probably at a level of a ppb level. So that's equivalent like a teaspoon of sugar pouring into an Olympic-sized swimming pool. So you probably say, oh, okay, that little amount, yes, I'm sure even that little amount of mycotoxin can make you sick. So that means you definitely don't want those compounds in your food. So next, we probably will do a further in-depth analysis that start with the sample prep. So in this study, we used a quick dilute, filter, and shoot method according to Dr. Kai Zhang's publication. It could be a universal method. That means you can apply this method to multi-class mycotoxins in different matrices. And also, like you can see from the flowchart, it's very easy and straightforward. First, you just weigh out 1 gram of your homogenized commodity and add 2 ml of water to soak the dry powder for 2 minutes or even more. Then you spike in your target mycotoxins at this step for QC samples. And then if you're using stable isotope dilution assay, you can add your standard, internal standard here. Then you can just use the formula of extraction solvent for the extraction, which is half acetonitrile and half water, vortex and centrifuge. Then transfer the top layer or supernatant to the filter. In here, we use something slightly different from Kai Zhang's paper. We use the Thomson single-step filter vial, including the syringe vial. In this case, it's easy and save you time. Well, just in case you're not familiar with this Thomson vial, I can briefly explain how it works. It contains mainly two parts, the bottom shell and the top plunger with the filter in it. First, you just transfer your top layer or the supernatant to the bottom shell. Then you just insert your plunger with the filter into the shell halfway down. At this step, you can either vortex, shake, or just necessary. And then you just press down the top plunger all the way down to the bottom of your shell. In this case, you filtered your sample. So as you can see, the vial is really small, so it greatly reduces the loss of your sample compared to the syringe filter, and it only consumes like up to 500 microliter of your sample. And this is also the final vial strict to your mass spec. And then we developed the LCMS method for mycotoxins by using the Raptor Biphenyl column. As you can see from the chromatogram, like all the 12 mycotoxins were resolved or analyzed in only 5.5 minutes. So as you can see, including two isobars, fumonisin B2 and fumonisin B3, they are fully resolved chromatography, and also the back pressure is relatively low. It's less than 4,000 psi. In that case, you don't need to worry about using a UHPLC or something. So for further information or details, you can refer our publication. It's an open access. So you probably will ask me, like, what is the success or what is the secret of your success? So I can share with you. The secret is this buffer. So as you notice that I added a 2 millimole ammonium formate buffer in both mobile phase A and B. Why is that? I can show you a comparison. In that case, you will understand it. You will understand why. So this is one of the examples that I did for tuning. As you can see, this is without buffer when I was doing the tuning for aflatoxin B2. The sodium eye duct is the majority ion or the predominant ion when I was doing the tuning. I barely can see the N plus H. So after I added my buffer, even with a little amount, only 2 millimole ammonium forming buffer, the situation switched completely, so it greatly reduced the sodium adduct. I should remind you that for most of the mycotoxin, it's the case, and except for HT2, T2, fumonisin B1, B2, B3, and orchotoxin A, there is no big difference between buffer and no buffer. I mean, like if you are if you are experiencing the same situation or you are having problems in seeing your parent ion, you probably can try this method. It also has been reported in other literatures too. So, so far, been talking about LCMS method, and actually there are also many other analytical methods have been developed for mycotoxin analysis, such as GCMS, SFC, TLC, immunoassays, and so on. But increasingly, LCMS is more and more popular. I think it's more suitable for this type of analysis because compared to UV or fluorescence detectors, MS allows the analysis or identification without any derivatization. In addition, mass spec also offers better sensitivity, throughput, specificity, and efficiency. However, there is one challenge that faced by the LCMS technique caused by the electrospray ionization. Okay, you probably will ask, okay, what is the matrix effect? Simply, I can explain it in this way. Matrix effect is caused by the junk from your matrix that co-elute with your target analyte. It causes the problem of enhancement or suppression of your target ionization signals, resulting in loss of precision and accuracy. Do I have any ways to solve this problem? Well, we do. In general, I categorize them into three different groups. First, we can do some sample prep to remove those junks from your target analytes as much as possible. But there are some problems for this method. One thing is there is no method can fit for all purpose. You probably can only target on one analyte in one specific in one specific matrix. So in that case, it's not fit for all purpose or multi-class method. The second method you can try is to develop a careful chromatography to separate those junk from your target analyte. But this method is kind of you're working in the dark. You have no idea about what the junks are or what the interference are, what the MRM transitions for those interference. And the third method is more universal. It's kind of like not removing them from your target analyte. It just uses some type of calibration methods to compensate the interference or matrix effect, including stable isotope dilution assay. In short, it's called SIDA, and matrix match the calibration, and also standard addition. Standard addition can be laborious and also cost a lot of time. So in today's presentation, I will mainly focus on SIDA and the matrix match. But overall, I think there is always a trade-off among all different methods. So it really needs you to think about what you really need to tailor your method in practice. And first, let me explain what is SIDA. SIDA stands for Stable Isotope Dilution Assay, and I can explain it in a very simple way. So here, this picture shows a gradient color of the solution. So I can use this to represent my calibration curve with like different concentrations of my target analytes. As you can see, I also spiked my internal standard same amount into those calibration curves. Well, here I would like to remind you that this is the calibration curve that I prepared in the neat solution or solvent, not in any type of the matrix. In this case, I build my calibration curve with the relative response of analytes and the internal standards. So then after I have my calibration curve, I can do my unknown. So those unknowns theoretically can be anything. It can be like a vegetables or powder of your like coffee or like a fruits. Yeah, it can be everything as long as you spike the same amount of the internal standards prior to your extraction. So in doing so, it is able to account for both the extraction and ionization efficiency. However, the tricky thing is this internal standard can be special, and usually it's stable labeled isotopic internal standard and matching to your target analyte. So I will talk about like this more in the following slides. And what is a matrix matched calibration? First, you will have your unknown samples that you don't have to use your corresponding internal standard. And you will extract your calibration curve like using a blank matrix. After extraction, you will spike in your target analytes into the calibration curve. In this case, you will use your calibration curve to back calculate your unknowns in the matrix. However, before you do the extraction or do the official like study, you have to make sure your absolute extraction recovery is ranging from 70 to 120. Oh, sorry. So you have to make sure the extraction recovery is ranging from 70 to 120. In this case, we ignore the loss during extraction, considering that's 100% recovery. And it could be laborious, honestly, because think about if you are doing apple, you have to prepare the calibration curve in apple. Then you have to do pear. Then you have to do coffee. That means you have to prepare every single calibration curve for each matrix. And while I'm always not good at making decisions, so SIDA versus matrix match, which method shall I use? This sounds a very hard question to me, actually. So it is very obvious. SIDA has a lot of advantages, such as the low consumption of your sample, and it's matrix independent. You can just generate one calibration and apply to all different matrices. Fast and easy, obviously. And also for those incurred analyte matrices, for example, it's very hard to find a clean matrix without any mycotoxin. In this case, you are not able to use the matrix match to calculate how much in the food, how much mycotoxins in your food. So SIDA will be perfect for this situation. Well, as I mentioned too, internal standard can be tricky because most of the time, like it might not be available for your target analyte, and even you can buy it, it's still very expensive. So as far as the matrix matched method considered, it can eliminate the cost or usage of standard, and it also minimize the matrix effect in a certain way. Well, as I mentioned too, it can be tedious and more time consuming. Even you save the cost for internal standard, but I think labor fee is another big cost and time consuming too. So for those like already contaminated with your mycotoxins or target analytes, it's very inaccurate to do the concentration calculation. And Usually, I mean, like a matrix effect is invisible. It's hard to see by eyes. It's just reflected by the enhancement or suppression of your target signals. Here, I found like a more visible example for you. This chromatograph has two parts. The top one is the HT2 spiked into the peanut powder, and the bottom one is just a blank peanut matrix. As you can see, the blank also has the primary M-arm transition for HT2, which is 447.3 to 285.3. Well, seems like an interference present in the blank matrix. So in this case, we were not able to do the integration or calculation according to this like a primary quantifier. So therefore, we selected a qualifier, which is less abundant M-arm transition 447.3 to 345.3 to do the quantification and the calculation. Well, as a result, as I mentioned that it's much less abundant, so I bumped my LLOQ from 5 to 10 nanogram per gram. And this only happened to the HT2 in this specific peanut powder. I guess there must be some co-extracted and co-eluted junk with this HT2. Okay, so here are the matrix match the calibration results, and a calibration curve with 100 times the dynamic range was built, and excellent linearity was observed with this method. So the recovery and the precision of this method were assessed using two QC samples, 100 and 200 for the top like analytes such as deoxyvolenol, phenols, B1, HT2, those compounds, and 10 times lower for aflatoxins and orchotoxin A. As you can see, the majority of recovery range from 70 to 120. Yeah, I'd like to mention one thing here is that this is the true recovery or absolute recovery showing here because the QC samples, 100, 200, those two QC samples were spec'd before extraction and compared to the calibration curve, which mycotoxins spiked after extraction. So ideally, I think while this method can compensate the matrix interference, however, realistically, matrix match cannot fully account for the different degrees of matrix effect. Here is one example. As you can see, the red numbers for the low recovery of aflatoxin B1 in brown rice. As you can see, it's super low, it's in 20s. So you may probably say, okay, maybe because the extraction method is not suitable for this aflatoxin B1. But look at this same compound in other matrices. Seems like they are all doing good. But maybe this is not a good method for this brown rice. But look at other compounds in brown rice. They are all at a very good numbers, 90 to 120, something like that. So what was the problem? I think that's the matrix effect. That's the signal that got suppressed by the co-eluted matrix interference and only affected the aflatoxin B1, in particularly brown rice. Wow, let's take a look at the SIDA method. Seems like it's excellent result and across all the four matrices. Look at the dynamic range, it's 1,000 times. And R square, all with more than 3 nines. And the accuracy above 90% mostly. However, something didn't look right. I know you will ask me this question. I have 12 mycotoxins, but why I only show 6 of them? Well, I have to be honest with you because when I first started this work, I would like to save some money. So I didn't purchase all the stable labeled internal standards for all the 12 mycotoxins. So in the hope that I can share some of the internal standards, I only bought those 6 internal standards. But turned out it is not good. It is really bad decision. And also, I was thinking maybe I can share the internal standard for other compounds, but turned out sharing is not always a good thing. I can explain why. So, just as I said, how do you know the method you developed is a good method? You have to do some tests using your reference material. Before that, I also used the SIDA method to do the incurred mycotoxins analysis because I only have 6 internal standards, so I only calculated those 6 in corn, peanut powder, and brown rice. So as you can see, seems like the numbers are okay, except the oxynivalenol slightly high, but I think overall it's still under regulations. I should say, thanks to SIDA method, otherwise I couldn't do this analysis using matrix matched. And now we are doing some reference material. I bought two different I bought 2 different types of reference materials from FAPAS and list back the 4 different mycotoxins in it. As you can see, the oxynivalenol, aflatoxin B1, orchotoxin A, and the zearalenone. So the middle column measured value is the a number that I obtained from my method. And the second column to the right, that's assigned value offered by FAPAS. So as you can see, the accuracies for most of the compounds are all above 91%, which is perfect, right? It's very accurate, except one compound. Why is that? Because as I said, I didn't buy the internal standard for this compound. So I just use a closely eluting aflatoxin G1 internal standard as the analog and to see if it could serve as a substitute internal standard. But seems like it's quite obvious it's not accurate and the results are not acceptable. And even they are the neighbors and they have a very similar chromatographic retention, they still cannot serve each other. And from here, I learned my lesson that sometimes for now it seems like you're saving money, but for the long term run, it could be more expensive, right? Okay, so here are more examples of why you don't want to share internal standards. The calibration curves without their matching or corresponding internal standards. They are quadratic and splitting the 2 calibration curve. The first one, the second one, they are splitting. But you probably say, oh, it seems like the last one look okay. It's linear and they are quite tight. Yes, the last one also used for calculation for the QC and unknowns. Turn out even the calibration looks okay, the results are not accurate. But I should say that this is a specific or particular case that we cannot use the internal standard to share. But for most of the clinical analysis, we always share the internal standards. So it's case by case, right? And next, by looking at the calibration curves with their corresponding internal standards, it's linear, wide dynamic range, and the 2 calibration curves, they are really tight. I only have one thing to say. It's worth of the money, right? So far, I've done all the series experiments or research. So after I established my method and tested my method to show accurate, I started to do something for fun. Now I bought some corn flour from grocery store, I usually bought to make a cake or a cornmeal. Then I did a test. I saw this chromatogram. Seems like I saw most of the mycotoxins at a relatively high level. I was totally shocked, and I know what brand is. I'm not gonna buy that anymore. Then I also have another story to share. I actually had his picture here, but like my manager told me, probably not using his picture, but still can share the story. My colleague, he is a huge fan of peanut butter. He usually has a huge jar of peanut butter in his office. And so one day I was thinking, oh, maybe I should test his peanut butter to show him that how much mycotoxins he's eating every day. Then I asked him, oh, can I test your peanut butter? He was like, oh, okay, but I don't want to know the results. I asked why. He said, because he believes that you're gonna die of something eventually. So he said, I'd rather not know. I said, okay. So after 20 minutes, I came back with this result. There is only one mycotoxin detected, and at a relatively very low concentration. So seems like it's safe. And I broke my promise. I told him the results. I told him it's safe. Then he was happy. He said, "Oh, I like my peanut butter again." He also shared these results at social media. So here, this is a very interesting story. Then you probably have questions for me like, okay, seems like so far you all did like a successful like results with your method. Have you ever gone through any like problematic matrix or obstacles? Yes, I do. I didn't show this in my like publication, but I can share the experience with you here. It is the wheat flour. So this wheat flour gave me problems when I was doing the Thomson filter. It hurt my thumb because the pressure you can feel. It's really hard to push the plunger down to the shell bottom vial. Then even I could do the filtration. It also clogged my columns many times. In that case, I killed a couple of my columns. I hope my manager won't hear this because I didn't tell him. So I feel like it probably needs some like a special filtration or something special, like some junk special stuck there. I don't know. So I stopped my working at that point. But when I was preparing this presentation, I was thinking maybe in future if I come back to do this work again, I probably can try some cold extraction solvent and freeze them like a lower temperature for a longer time. Hopefully, by doing so, I can just remove some of the junk. I guess might be proteins or some other like interference. So hopefully, my experience can help you, or if you are experiencing the same thing, please feel free to contact me to give me suggestions, or we can talk about this together. And here comes the conclusion. So we developed a better, faster, and simpler LC method using the Raptor Biphenyl column, and the total analysis time is only 5.5 minutes. So the 12 regulated mycotoxins in 4 different matrices were studied by 2 different calibration methods. I still prefer like a SIDA, stable isotope dilution assay, over other methods because it's more accurate and easy, although you probably need to spend some money on the internal standard. But still, matrix matching is another alternative if you don't have the internal standard available. And also, this internal standard again is very important for SIDA method. So you better match the chemistry of the target as much as possible. Otherwise, you probably will have inaccurate results as I observed. So it seems like my method is really accurate for those compounds, which I have the internal standard. And finally, I would like to give my special thanks to Dr. Kai Zhang from FDA for his great support of this work. And thank you for listening. I will be happy to answer questions if you have any. Thank you.